Okay, welcome everyone. Let's look at ERM on neural networks. So we start with x in RD and y in some RK, make it R also. So we have data as usual, which are samples drawn ID from the distribution. H theta of x is the neural network, the W1 times x sigma here and W2. Let's say we have this neural network for ease. So we need our theta star to be equal to the minimal argmin of the empirical risk, which is 1 over n, I is 1 through n. We have some loss function psi comma yi, right. This is our standard ERM that we do. Now how do we do this? For neural networks we use the gradient descent. We have already seen what gradient descent is. This is some alpha times we have the empirical risk. Let's call this r cap of theta. It's a function of theta. R cap of theta, take the derivative of this with respect to this is standard gradient descent that we do, right. Now what is important is how do we compute r cap, the derivative of r cap theta with respect to theta for these kinds of functions, right. The question, so how to compute the gradient of the empirical risk with respect to theta for neural networks. The solution is the chain rule. Composite functions are, the gradients of composite functions are computed using chain rule. We all know that, right. The gradient of e power sin x squared, start from the innermost function, take the derivative, keep hopping, right? That is exactly what we do, okay. See, chain rule for neural network has a fancy name, it is called error backpropagation. And we will work uh, the backpropagation algorithm now. This is the algorithm that the Hinton came up with, right. So it's sort of made the community train neural network, so to speak, or I mean you know what training is, it's simply doing gradient descent within ERM, okay. Let's look at chain rule for these kinds of composite functions that we have, which is called the error backpropagation algorithm. See, to do that, just to ensure that that you appreciate the equations that are there, no, I will resort to the scalar form. Even though the implementations, standard implementations today are done using vectorized operations, I will do it assuming, I will resort to the scalar form when I work out the backpropagation, because it's called error backpropagation for a reason. So those kinds of nice equations come out only if we look at the scalar form of things, okay. So let us work error backpropagation. So this is backprop for a neural network. So there is a lot of notations, I will just write that notation now. So notations. So maybe before I write the notations, I will write the diagram. So we have data which is x, which is in RD, right. So we have d dimensions of it, 1, 2, 3, 4 up to. So this is x in RD. So note that I am now using scalars to do everything, okay. So there are a few neurons here in the first layer, neurons in the second layer, and so on, okay. Now what happens is I will take this as the lth layer, L, or we will take this as the lth layer. Hold on, just do not write yet, I will complete the notations and then you can copy. This is L minus first layer, Lth layer, and we also need an L plus first layer. Okay. Then what happens is that this is connected to all of this neuron, and this is connected to do you see what is happening here? Okay. So, in our vectorized notation, see, please note that every dimension of data here is connected to one neuron. You see what I am saying? Every dimension of data here, right, is connected to all neurons individually. Okay. Now, in our vectorized notation, that forms one column of the W matrix. So, every layer of neural network will now have one W matrix. Okay. And how many columns will this W matrix have? It will have those many columns as there are number of neurons in a layer. Okay. All data dimensions connect to every single neuron, okay, whose weight with the weights that are given by one column of the W matrix that defines a layer. Is this clear to all of you? Okay. And there are as many W matrices as there are number of layers. Now, if I write all these connections, the diagram will look very messy. That is why it is called a neural network. Have you seen that diagram, right? I mean, they show that there are so many connections that will happen. So, it will look like this if you want me to do. This is connected one neuron here, right? And there is you see what I am saying? This is why it is a neural network, so to speak. Yeah. That is a hyperparameter. How do you choose the number of neurons in every layer? It is a hyperparameter, that is a design choice. Okay, there is no one typical answer to it. See, please note that if you look at this part, right, the output of this particular layer can be seen as input to another neural network that is going on. I mean, that is the nature of any composite function, right, that is how it works. Is this clear? Okay. So, now this is how it is. Let me write down the notations. So, let L, so notations. So, L is the current layer, so J is the index of a neuron in the Lth layer, okay, and K index of a neuron in the L minus first layer. Understand, right? And let us say I is the index of in the L plus first layer. Now, this is important. We have W, J, K, L. This is weight connecting neuron K to neuron J. Please note that neuron K is in L minus first layer and neuron J is in Lth layer. So, WJKL is the weight that connects K to J. So, this is how it is, right. So, index of this is in L minus 1, K to J, yeah. So, let us say that this is the neuron that we are talking about, it becomes too messy. So, if this is the K or J, what is this? this is J, this is jth neuron and this is kth neuron, okay, and there is a weight that connects these two, and this is W jk. So this is an element of that particular matrix that we are looking at. Is that all right? Also note that the elements of the column of this matrix that defines a particular layer, okay, those contains the weights that connect a particular layer in the next layer, next neuron. All those weights are stacked into a particular column. Okay. If you are looking at scalars, then there are these many connections. W, J, K, L defines the weight connecting neuron K to neuron J. Is that all right? Okay. So we have so B, J, L is the bias of neuron J in layer L. Okay. Now let me define a few more things here. Define ZJL as follows. JKL AKL minus 1 plus BJL, and this is over K, where AJ of L is sigma of CJL. Okay. So now these two things are called the activations and the pre-activation of a particular neuron. What is this? See, what is this operation? This operation is W transpose X, right. So now we know that the kind of operations that every neuron does is take the inner product and then pass it through the non-linearity. Okay. So we will define a variable called this pre-activation output, okay, which is simply the linear projection of data before the activation function or before the non-linearity, and whatever comes out of the activity the non-linearity is called the activation of that particular neuron. Is that all right? So this operation is nothing but W transpose X, right? That's exactly what it is. Now let us with this, and by the way, please note that for the first layer, this AK or AJL is simply the input. Is that all right? Okay. So let us define this. So now ZJL be the pre-activation output of neuron J in layer L. And we have AJL is the output or activation. It is also called activation or output of jth neuron in the Lth layer. Is it all right? Now notations are clear. Let me just flash them again so that we are all on the same page. Any questions on notations? Now what do we want to do? We now have to find the gradient of the empirical risk R cap with respect to all these W, J, K, Ls. That is what we will do now. Is that all right? See, why did I write it as a scalar is because when you write chain rule for multiple variables, right, do you know how chain rule applies for multiple variables? You have to take the derivative, with respect to each path and then sum them through, right. So that comes up only if you write it as an explicit summation here. That is why I wrote the scalars. Let me write that. Notations are clear. Let's move on now. Okay. So now there are uh, two things that one needs to do, okay, when you compute the gradient. Uh, let's to compute the gradients. Suppose R cap denotes the empirical risk. Okay, we want the derivative of R cap with respect to W, what was that, JKL. This is what we need, correct? If we get this, then we can do it for every each of the parameters and then do the gradient descent, correct? We want this. So to do this, let us define the error for a single neuron in layer L as follows. Delta JL. So write this as the derivative of R, the function that we are trying to take the derivative with respect to, this is with respect to this. Okay. So let me just give you an overview of how we go about solving this problem before we go with the algebra. See, the idea is very simple. Now here is where we have after many layers we have to compute R cap, right? I have to compute the R cap. Now if you want to find the derivative of R cap with respect to some weight here, the dependence of this particular weight on R cap is through every path this WJK has seen till R cap, isn't it? Right? So we have to traverse that path, that's all it is. So that's what chain rule does, isn't it? If you have a composite function, if you want to take the derivative of the outermost function with respect to a variable that is inside the composition, then you traverse the entire path back, that's the whole idea. So to do that, what we have to do is that we will have to come back, I mean that's why the name back, we will see the algebra very nicely. So we start to take the derivative of the loss function or the empirical risk with respect to the pre-activation, which is Z. Okay, then we use this to compute the derivative of this with respect to the layer before it and so on till we reach that Wj, that is the idea. Okay. So let us do that, let us do the algebra. This is a very important variable, this is the derivative of the empirical risk R cap with respect to the pre-activation of the neuron J at layer L. Is that all right? Okay. So this is very well valid because this ZJL is a function of Wj, right, and the R cap, the final R cap will be a function of ZJL as well. Do you see that? Okay. And by the way, what is R cap? So we know that R cap is h theta of xi comma yi, correct? Now since h theta depends on Wjk and it depends on Zj, and that is why the derivative of R cap with respect to Zj is well defined, correct? Yeah. Okay, so let us look at this. Now to compute, and by the way again one more point to be made is the way we will go about this attack this problem is we will establish a relationship between this error component in the Lth layer and the error component in the L minus first layer. You see what I am saying? So this so called error is now defined for every neuron in each layer, isn't it? Okay. Now what we will do first is that we will establish a relationship, okay, between the error in the L plus first layer and the error in the Lth layer. Okay. So to reach to the derivative of or rather to reach to the weight of jk at the layer L, we will do it through the error in the layers that come after that. You see why it is to be done that way? Because the empirical risk is computed at the final layer. The dependence of this empirical risk, or rather the dependence of the weight in some layer in between on the empirical risk, is through every neuron that comes between these two. And therefore, if we compute the error with respect to the last layer and then relate that error to the error in the previous layer and so on, perhaps we can reach to the gradient of this loss with respect to a neuron that is in some intermediate layer. That is the idea. Now, the first thing that is to be done is we will have to compute, or rather we will have to establish a relationship between the error in the Lth layer and the error that is computed in the L minus first layer and so on. To do that, we will have to start by computing the error in the final layer. That is what we will do now. Is it clear? Okay. So, to compute error for the final layer, capital Lth layer. So, to do this, we will have to compute del JL. Note that we do this for every single neuron, right. So, this is del R cap by del ZJL. This is equal to this is okay. Why is this the case? The dependence of R cap on ZJL, right, can be written through A as well. And please note that A capital L is the output of the neural network. H theta of x is equal to AL. You see that? Maybe just write, let me just write that. By definition, correct? Yeah. Because there is an activation in between, no, we will just see that. We will have to take the derivative of that as well. Let me write that. So, now this is equal to the activation that is computed on ZJL, the derivative of this with respect to ZJL is simply the derivative of this. Do you see this? See, since AL is simply, or yeah, this is ALJ, okay. The derivative of ALJ with respect to ZJL is simply the derivative of the activation computed at ZJL, correct? That's obvious. See, since we are looking at derivatives of the activations, no, these functions have to be differentiable. Okay, you see this? So, we got this particular term. So, now we know how to compute this particular term. What about the first term? Depends upon the last function. So, now first term, let's do that. Now, del R cap by del AJL can be computed. Why? Is the derivative of I think it's better if we do it for single data point, right? So, already too many this thing. So, this is equal to ALJ minus loss computed, not minus, hold on, just do not write it, ALJ, and you have YJ, the J component of the particular output. You see this? This is what it is. depending upon what your loss function is, you compute it this way. And this can be computed because we know what the loss function is, and depending upon what the loss function is, this can be computed. Let me write this. Come again. I mean, assuming that y is a vector, I am talking about the jth component of the y. If AL is also a k dimensional vector, y is also a k dimensional vector, so loss is computed dimension wise. I mean, that is why I have written as derivative of this with respect to A, L, J, all are scalars right now. Make sense? Yeah. So can be computed. See, now this means that we now know how to get this del Lj, correct? So whatever we are computing, let me just put a tick mark there. So this, we know how to compute this now. Is that all right? Okay. So now let's, to compute the error that is there in some hidden layer, lth layer for the jth neuron. See, the algebra seems a bit clumsy and involved, but all we are doing is chain rule, repeated application of chain rule. Okay. So now we will do that. So we know that del Lj is the derivative of the pre-activation of the jth neuron in the lth layer, correct? Now please look at this. So dependence of the output R cap, okay, on ZLJ is through multiple variables that come in between R cap and the lth layer. Okay. So now if you have a composite function and the dependency of the output is through multiple variables and there are multiple paths, parallel paths, then multi-variable chain rule tells you that you will have to add the partial derivatives along all those paths, correct. So now let us do that. Now let me write that down. Yeah, so this should be the derivative of the activation, what index do I use? I, J, K, L, everything is taken. M is already taken. T huh? T is already taken. No. If it's not used now, we can take M. So this is M in L plus 1, and this is del Zm L plus 1 Z J L, and this is summation is over M. You see this? What am I saying here? The dependence of R cap, okay, on ZLJ is through every pre-activation that comes in the layer L plus 1. Does it make sense? Yeah. So then you have to add all those partial derivatives that come along the path. Is that okay? Okay. Now what is this equal to?
M will go from
1 to the number of neurons in the L plus first layer. Okay. Okay, good that you reminded me. Thanks. Yeah, I is already there for that in our notations. On a lighter note, when you are doing algebra like this, error in my brain gets propagated through. Is that okay? Now we already know that this term, the first term, what is the first term? First term is del L plus 1 I, yeah, it's correct by definition. And to compute the second part, let's look at what the second part is. Consider what is this equal to. To do this, we will have to write Zi L plus 1 is given by J Wij Ajl plus Bil plus 1. So we wrote all this very carefully last night, so that the indices should not be mistaken. Okay. Now this is equal to Wij L plus 1. What is Aj? Aj is sigma, because we need it in terms of Z, no, plus B I L plus 1. This is Zi L plus 1. Okay. Now if I take the derivative of this with respect to Zi at L, what will I get? Wij at L plus 1 times the derivative of this sigma dash time evaluated at ZLJ. Is this alright? Why is this the case? Because all the other terms here go to 0. You see that? Why is that the case? Because yeah, the dependence is only on one particular weight and everything else will go to 0. So we got this particular term as well. Okay. Now here was J. Was it J? Yeah, it is J. Thanks. Yeah. There is an idea called mixture of experts in LLMs, or rather even in neural networks, committee of experts. We will see when we look at boosting algorithms. So this class is like an MOE. If one makes a mistake, the other will point it out. That was a joke, by the way. Okay. So now we got this. Why did we do this? We'll have to substitute this here, right? So this implies our so del J L is now summation over I L plus 1 times Wij L plus 1, suddenly I put bracket there, okay, into evaluated at ZJL. See, this is the most beautiful part of backpropagation, okay. Look at what's happening here. If you ignore this particular term, okay, all we are saying is the error associated with the neuron, the jth neuron in layer L, okay, is the linear combination of the error associated with all the neurons in the L plus first layer, and the linear combination is weighted by the weights that are connecting the layer L and L plus 1. You see that? See, if you look at the data flow from the input to the output, at every layer the activations or the pre-activations are given by the weighted linear combinations of the activations in the previous layers. This is the forward pass. While you are computing the error, The errors also get linearly combined, okay, but in the reverse direction. That is why the name. The errors are propagating in the backward direction, right, and the propagation is weighted by the same weights that propagate the data from the first layer to the last layer. That's why this equation is so elegant. You see, so errors are getting propagated backwards because the error in the layer L, okay, is given as the linear combination of error in the layer L plus 1 weighted by the same weights that connect the neurons from the layer L to layer L plus 1. And of course, there is this term, just ignore it, I mean, for the sake of interpretation. Does it make sense? Yeah, that is why the name error backpropagation. Yeah, error gets propagated backwards via the weights, and therefore the name backpropagation. Okay. No, small l is capital L is only for the last layer. Everything else is small l. Oh, does this look like capital L? No, this is small l. That's small l. Yeah, capital L is only for the last layer. Right? This is for all layers. Once you see, basically the idea is you compute the error at the last layer and then use this recursive thing and backpropagate it, right? So once you have this, so finally to compute, so finally we want r cap, the derivative of this with respect to this thing, right? This is what we wanted. Now that's given by again use the chain rule, the dependence of this is through the activations times del ZJL divided by del WJKL. And what is this? This is okay. Do you notice notationally I have been using this dou for derivative and delta for the error. Do you notice that? Okay, I have been consistent, right? Okay. This is del L, and what is this? The derivative of that's actually pretty easy. What is that? That's AKL minus 1. Please verify that. It's pretty simple because this is given by sum over no, AK is given by sum over all this, right? No, ZJL is given by the sum over this AKL minus 1 and this multiplied by WJK, and they take the derivative, only that particular term will survive, and that's why it is this. Okay. Now we know both of this. Do we know del L delta Lj? We know how to do it. This is computed via backprop. This is in fact computed via what is called as a forward propagation. That is it. So this completes backprop. So we have the gradients that we need and then do a gradient descent. So summary is as follows, right? So let us say that we have a neural network that we build this way. Now I will vectorize. This is x. We have the first layer W1, we have W2, we have W3, and we have y here, which is h state of x. Do you notice that the length of the lines that I have written are decreasing? So, typically when we solve classification and regression problems, the number of neurons progressively will keep decreasing. That is the typical choice, okay, because typically what happens is the dimensionality of the input is much lesser than, sorry, the output is much lesser than the input, right. So, you keep decreasing the dimensionality and so that your output layer matches that of the output variable. Now, to get one gradient step, okay, so we will write that to get one gradient step. So, two things have to be done. So, first you do what is called as a forward propagation. Why do we need forward propagation? To get AL or the output for that particular input. So, once you get this, what do? Do one step of is that all right? So, to get one gradient step, we have to do one forward pass with a given data point, get the output, compute the loss and then do one full backward pass, okay, to obtain the gradients. Now, this is for one step of the gradient descent. So, basically the computation will get doubled when you are training. This is training, this is basically ERM, right, ERM on a neural network. One forward pass, one backward pass is one gradient step. By the way, when people implement gradient descent today, all of them are vectorized. Otherwise, these summations, see, you see this, right, the kind of operations that we have here are simply linear products, linear combinations. All linear combinations are vector multiplications, okay. Now, if you want to implement this as scalars, then you will have to write for loop over I, that is too much computation. Instead of that, you can implement all of these as vector inner products basically, right. So, you vectorize it and that is how you implement them. So, these GPUs are specialized hardware that will do these kinds of operations, which is vector products. They are designed to do these kinds of operations, and that is why they are very efficient. Okay, they are all matrix vector multiplications and sums and products, that is it. Okay. So, this is how backpropagation is done. So, every data point you take it one forward pass, compute the output and then backpropagate the error using this particular equation here, layer by layer. Then you compute the gradient and everything else is the same. This is training a neural network, and as I already told you, when we do it, when we use, let us say, stochastic gradient descent, do it over batches, and one complete pass through the data set that you are given is one epoch, and multiple epochs of trainings are done typically. Even your the latest LLMs are trained this way. What changes is the architecture, that is it, and the scale of data, but the essential training procedure is this error backpropagation. Okay. Any questions on this?
Do we do the epochs only on the back routes?
No.
Forward routes?
No. See, for every data point, see, you to do one gradient step, you will have to invariably do one forward pass and one backward pass. No, if you do not do the forward pass, you can't compute those gradients at all. That is precisely what we saw today, right. To compute the gradient, you will have to find those error terms. To find the error term, you will have to find the error term in the subsequent layer, and to do that you need the output. So, take a data point, get the output, compute the error and get the error of the previous layer, and so on, and the derivative of the parameter with respect to the loss is dependent on this layer at the error at that particular layer through the equations that we saw. So, to get the gradients, you will have to do one forward pass and one backward pass. Okay. Is that all right? So, this is the famous error backpropagation algorithm, which is the workhorse of all the AI models that you see today. But as I said, the scale of the data and the scale of the number of parameters is humongously large. And by the way, when they say that they are training neural networks or training these AI models for 6 months over the data centers that have tens and thousands of hundreds and thousands of GPUs, all they are doing is running this error backpropagation algorithm. Okay. So now if some of you can actually come up with an algorithm that would reduce the computational complexity of this and can be done without matrix multiplications, then the monopoly of some of the companies will be just gone. So I keep saying, right, some of these companies are one good algorithm away from bankruptcy. Their hardware will not be sold at all, right? Everything is I mean, there's so much demand for those hardware because all you are doing is doing vector multiplications, and those hardwares are built specifically for vector multiplications, right? So if there is a way to do ERM on these kinds of composite functions without vector multiplications, then of course you may get a Nobel Prize as well. Okay, so this is about error backpropagation. This is how you do ERM. So next time when we come, and by the way, just to complete the story, you can add regularizers to this loss function and nobody is stopping you. You see, so loss function plus let's say any kind of regularizer you want, and the same thing happens, same thing applies. The only thing is the gradient will change. To obtain the gradient with respect to the composite function which is the neural network, you need backprop. For the gradient of the regularizer, you don't need backprop. You can just compute it and then add it. Only the gradient descent equation would change, because gradient is a linear operator, right? If you add one other term, the gradient will just get added up, so it doesn't matter that way. You see that? So you can train a neural network with regularizers as well, explicit regularizers as well. So all the problems that I've given you in your assignment can be now solved using neural networks. The only thing is you'll have to code up backprop. I will ask you to code up backprop as well as a part of your next assignment. Okay, so that's it. Next class, what we will do perhaps is I will talk about different architectures and how you can see architectural. Remember, I told you that any kind of choice that we make on H theta can be viewed as Bayesian regularizers. I will show you that convolutional neural network is actually a regularized, heavily regularized MLP. Yeah, we will see a couple of architectures, maybe CNN, RNN, and transformers, and then we will move on to the other algorithms, the ensemble methods, and so on. Okay. Okay, thank you. That's it for today's class.